It gives me great pleasure to introduce my colleague and friend, Professor Nazario Martín. He is a full professor at the Complutense University in Madrid and vice director of the Institute MDA Nanoscience, the famous Nanoscience Institute in Madrid. And his research interest is very broad, but it's based on electron transfer process, and we all know how important it will be, and we hear a lot about it during his talk. But it's in the context of carbon nanostructures, biomedical properties, chirality, photovoltaics, and much more in the nanoscience field. He has he has received numerous awards. It's a long list. Yeah, I will not give the whole list, but just mention that he has the Alexander von Humboldt Award, which is very prestigious, and more recently the National Award in Chemistry Enrique Mols in 2020, yeah, which is also a very prestigious prize in Spain, I think. The topic for today is facing the energy challenge, yeah, and he focuses on perovskite solar cells, and we all know this is a really important problem, and we have seen amazing success and progress and discoveries in the past 10 years. So it's with great pleasure that I introduce him. I have to mention we are now, since last year or so, both members, he was for a long time, but I was inducted in the Spanish Royal Academy of Science, and it was great to meet all the friends, and I meet them at many occasions. And this year is special for us because we both like aromaticity, I mentioned it, and we look forward to your talk about perovskites towards solar cells. You can see the title here. Nazario, the floor is yours.
Thank you so much. Thank you, Ben. Okay, so first of all, I would like to thank the organizer at the local committee, the international committee, and particularly to Jorge Mendez for organizing this fest, okay, scientific fest. Not only scientific, by the way. My presentation was already said by Ben, facing the energy challenge, perovskite solar cells. Okay, but before starting with this topic, let me introduce a little bit our science, our current interests, our current topics in our group in Madrid, which is, as it was mentioned, at Complutense University, but also at the Indian Nanoscience Institute in Madrid. We have been engaged with the carbon element. This is probably the most promiscuous element in the periodic table. And we have developed during maybe the last decade, the last 2 decades, a lot of studies related on carbon nanostructure, covalent chemistry, supramolecular chemistry, organic electronics involving different kind of carbon structures, very successful on-surface synthesis that we are developing at Indian Nanoscience Institute with physicists over there, with the STM equipments, non-contact AFMs, and so on. And also chiral graphene quantum dots. This is one of my favorite topics because, as was mentioned by Ben, chirality is something which is really exciting from many viewpoints. Also, we have applied these carbon nanostructures to biomedical applications and photovoltaics. In particular, we participated in the first European project devoted to organic solar cells. And since then, there were always a project in Europe devoted to this topic. That was in the mid-90s. But currently, we are engaged with perovskite solar cells, and then to conclude, the carbon nanodots as another topic in our group. Okay. Today, photovoltaics. And since the beginning of Industrial Revolution, progress has been intimately connected with the use of fossil fuels, with the concomitant problems stemming from this pollution. But look at this, the Industrial Revolution brought the factories as a new way of production, and but also interesting things from a societal viewpoint, like public lighting in the cities, the steam engine with where railways and also cars were the result of this. But today I would like to focus specifically on these figures, on these numbers, because the population increase in 2 centuries from 1,000 million million inhabitants to roughly 7,000. And today, what is really to be worried is that at this rate, in 2050, it could be around 10,000 million inhabitants. So no doubt, energy is currently one of the most important problems facing mankind. Okay, this is in order to prevent the disaster of the contaminations in the planet. There is the United Nations are organizing since a long time ago the climate change conferences with different results, because maybe the most important one was in Paris in 2015, where it was considered the global warming to keep it below 2 Celsius degrees. And there was another one in Madrid recently, or more recently, in 2019. And the idea was to keep the emissions to 0 by 2050. Well, this is for future. And in Glasgow 2021, look at what the President Alok Sharma said. It was at that time considered 1.5 degrees, the warming of the planet. And he said, we can now say with credibility that we have kept 1.5 degrees alive, but its pulse is weak, and it will only survive if we keep our promises and translate commitments into rapid action. So this was claiming this necessity. But look at, this is the current situation. This is the last one in 2024, was held in Baku in Azerbaijan. And the idea was, this was the conclusion, to adopt a new global climate finance goal with the developed nations pledging at least $300 billion annually to contribute to the global fight against climate change. This was the idea, but look at what is the situation. If we want to reach these challenges, of course, further development of renewable energy are required. And what is the current situation? The current situation is that during the around 175 years, the planet temperature has risen to 1.5 degrees Celsius degrees. And what Mr. President Trump said? Well, he likes to sign many documents, as everybody knows, all over the world. An executive order to withdraw the US from the Paris Agreement, a key component of the United Nations Climate Action Framework. This action means a rejection of the conference's conclusions and a shift away from international cooperation of climate change. This is from the US. Also, well, maybe a little bit more positive, what is coming from China. China, the world's biggest source of planet warming gases, has for the first time committed to an absolute target to cut its emissions. This is the first time China declares this. The president said that China would reduce its greenhouse gas emissions across the economy in between 7 to 10% by 2035, while striving to do better, okay? Striving to do better. But they declare carbon neutrality for 2060. This is the current situation. It's a little bit worried. Anyway, let's go to science. These are the most important renewable energies in the world. And focusing on solar energy, probably most of you know that photovoltaic is considered as, or among the most promising energy alternatives. And well, there are many of these data in the internet. But just if we were able to harvest around 0.02% of the solar energy reaching our planet, that would be more than enough to satisfy our needs. just to give you a number, this is what the world power in 2023. It was, we spent in all the planets 620 exajoule. One exajoule is 10 to 18 joules. And just to give you an idea about what kind of energy that is it is the energy produced by sun in 1 second. Okay? So this is interesting. And if we consider, which is the projected world energy mix for 2030, it's a little bit, well, let's say renewable is around 14, and here is with a 5% the nuclear power. Nuclear power is now considered a kind of green energy. When I was a young boy, it was considered just the opposite, but you know what, with the time, things change drastically. So, but what is amazing is that the coal, gas, and oil represent the biggest one. So, what about, this is for 2030, which is not certainly a big improvement. Okay, let's go to photovoltaics, start the best one, or the beginning of this study in 1954 in Bell Laboratories with these three scientists, Chapin, Fuller, and Pearson, who obtained the first silicon solar cells with an efficiency roughly around 6%. And well, it depends. Today, it is the most important market in photovoltaics, and it depends on the silicon and polycrystalline or monocrystal. That is the difference is much more expensive, the last one. So, but if you go to all other advanced solar cells, mostly what are considered all organic solar cells, hybrid or great cell solar cells, small organic molecule, or even perovskites, all of them have something in common, and which is the presence of organic materials. Organic materials are present in all these solar cells for different purposes, okay? But this is the argument, because organic synthetic chemists are also inside this field. Well, as Ben said, we must be proud of being chemists, okay? So, and without our participation here, that would be not possible. So it's as simple as this. So the content of this, that would be, because not everybody in the audience is connected with perovskite photovoltaics, I would like to make a general consideration, introduction to the field, and then to go specifically to our molecules, had been prepared by using chemical protocols, star-shaped chalcogenides, and in particular the so-called benzo-3-thiophene, the BTT, or by modifying the thiophene by other heteroatoms like pyrrole, well, this is nitrogen, oxygen, or selenium. And from here, I would like to show you our most recent results, which are recently really amazing, according to the stability and also the efficiency of the cells. So the motivation for this is just to have a better understanding of the interaction of the perovskite with other materials, particularly hot transporting materials, in the search for efficient and stable cells. Okay, which is a revolution. Perovskites mean a revolution. This is clear because from the very beginning, it was considered by the scientific community in this way. Just to show you which is how is the state of the art in these systems. Silicon, this is the largest efficiency reported recently, around 27%, just for 350 square centimeters, so which is really amazing. And also dye-sensitized solar cells is around 14%. Organic solar cells recently surpassed 20% efficiency. These are world records, okay? And what about the perovskites? Recently was reported around 27% and was certified 26.7. So this is really interesting, and if you consider the possibility of tandem solar cells, including perovskites and silicon, efficiency is close to 35% has already been achieved, which is quite interesting. Something of interest just to show you, if you take a solar cell, silicon solar cells, the thickness of the photoactive layer is roughly 200, 300 microns. But if you go to perovskite solar cells, the thickness is roughly the same number, something like 300 nanometers. That means 3 orders of magnitude less material than the other one. So this is to take into account. Just to give you this idea, the number of papers published in 2024 surpassed 4,000. So it's impossible to follow the bibliography in this topic. So this is one of the drawbacks of working in this field. Because many people talk about perovskite. Some people think this is a kind of Russian dessert or something like that. It is not. It's a mineral, okay? And the mineral was discovered by Gustav Rose, and he was studying this calcium titanate. This is a salt. So salt is soluble in water. So take in mind, because this is the main problem of perovskites. And it was called perovskite because Lev Perovsky, a Russian mineralogist, was a very good colleague from Gustav Rose. So he gave this name, and the stoichiometry is ABX3. I will explain you later on. These are A and B are cations. X is the halogens. And typically it's a cubic structure, but there are other variants. The size of the cations are very stringent in order to preserve the stability of these systems. And what is amazing in these so-called hybrid organic-inorganic trilite perovskites is that, typical cations are, the biggest cation is A in blue, and this is methylammonium, formamidinium, cesium, although it is not organic, but, and the other cation B typically is lead. Cations are with 2+ charges, and tin, bismuth has been used, although not particularly very successfully for this purpose, and much more recently copper too as well. And halides, you can use these 3, iodine, bromine, chlorine, or a mixture, which is typically more frequent. So the interest is that if you consider this FAPI, this is formamidinium, lead, and a mixture of iodine and bromine, you can see that if when Y is 0, that is only bromine, the absorption is really narrow. However, if you increase the presence of iodine, then you can reach even the absorption is occupy all the visible region. So it is very simple to modify, to tune the absorption properties of these materials, as you can see. And there are several important features. I will not go very much into detail, but look at the long charge carrier lifetime is over 100 nanoseconds, which this provides the opportunity for improving the efficiency, and the long diffusion length, so the carriers can survive over 1 micron. This is tremendously larger than the inorganic photovoltaic organic solar cells. And then also the binding energy in the exciton, in between the electron and the hole, are really, really small. So for silicon is roughly around 15. So that means that the exciton dissociate in the semiconducting material. This is a very naive way to show you what it is, how the photovoltaic cell is working. This is what people thought at the very beginning. So the idea was, in a perovskite, the behavior would be similar to the organic material. So when you have the photon is coming and then the exciton has been formed to dissociate the negative and the positive charges, you need a potential. That is at the interface. But this is for organic solar cell, but not for perovskites. Actually, for perovskite, like a semiconductor, a good semiconductor, that means dissociate within the photoactive material just to go to the electrodes. So, and this could be very, the reason is these values. Very short binding energy and very long diffusion time, length. Okay, so they are just when you excite the perovskite, these are the charge transfer processes occurring. So from here, the perovskite inject the electrons into the titania, and also at the same time, the holes are transferred to the hole transporting material. These are the green paths or pathways, but then there are other red pathways which are negative, and this is one of the reasons because the efficiencies are lower than expected. Okay, there are many at the interlayers occur many of these recombination processes. Okay, let me introduce you to Professor Shutomu Miyasaka. He was the first which used perovskites for photovoltaics. And here the first paper was published just in 2009. So perovskites are being under study relatively just 15 years ago, okay? And look at here. So he used the methylammonium, lead, and tribromide or triiodide. So the difference was almost one order, so almost around 20% better efficiencies for the iodine. The reason is that, as I showed you, the absorption involves the whole visible region of the spectrum. And this was the first papers published. And since then, you have seen the number of papers that have been published as well. So basically, for understanding, when you prepare a device of perovskite, there are two main architectures, what is called mesoporous. In the mesoporous, the titania is together with the perovskite is embedded in the titania, or the planar structure where you have perfect layers, okay? This is transparent conductive oxide. This is a transparent electrode, so when the light is going through, and then the electron transport layer, the photoactive material, the hole transporting material, and the metal electrode, okay? So when you have the planar structure, which is considered NIP as the normal one, N is the negative electron transport layer, I is the intrinsic or undoped material, this is the photoactive material, and P the positive hole transporting layer. So we have been very much interested in hole transporting layers along this time. But if you go to the reverse cell, then you have to change the order, and the hole transporting material is close to the transparent electrode. Therefore, you have to change. In order to keep the energy alignment, you have to change the materials, and that is what you do. Here with fullerenes or electron-accepting materials over there, and the electrode usually change from gold to aluminum or silver. So these are some of the here is, let's focus on hole transporting materials or hole transporting layer. The idea is to do that. Once the photon comes to the photoactive perovskite, it is generated, the electron and the hole. The electron goes to this ITO electrode, the transparent electrode, and the hole goes to the gold electrode. So here is the hole transporting material in green, and what this material must do is just to allow the transient of holes to the electrode, but also to prevent the movement of electrons, okay? These are what they must do. And the most used material is this one, which is called spirometat. This is the name, the chemical name for those who likes to follow the IUPAC names, okay? There are some advantages. This is a wide bandgap for this material. Everybody, so I would say 80% of the studies on perovskite have been done with this whole transporting material. It's interesting because of the energy alignment, dissolves well in organic solvents, and this is the semi-crystalline with the glass transition temperature at 125. But there are many important drawbacks. Low mobility, low conductivity. The synthetic protocol is complex. And actually, you have to purify the material because this is chemistry of materials. Purify the material by sublimation. This almost prevents their use for practical purposes or industrial fabrication of cells. So, if you want to improve the conductivity properties, then you have to add dopants. With this, the cell is much better, but the problem is that the stability decreases drastically as well. And yeah, it's a little bit slow. Okay. Here in this slide, there are some, most of the papers we have reported on whole transporting materials. And all of them are based on chalcogenide, oxygen, sulfur, selenium. And this is because of the beneficial interaction of these elements and the size of sulfur and selenium as well. So let me give you just a couple of examples of these systems. And you see that in all of the molecules we synthesize, there is a perfect alignment with the spiro. This is the reference, spirometat, as I mentioned you. And these are the monocation, dication, and trication perovskites. So this energy level must be in between the HOMO of this, or the valence band of the perovskites, okay, and the electrode, the metal electrode. And this is fulfilled by these systems. So let me show you a couple of examples from our group. We decided to go to benzo-3-thiophene. If you go to this molecule, this is the central core. But if you go there, there are, in principle, well, there are one benzene ring with 3 thiophenes fused to the central benzene ring. So, but the question is that there are 7 possibilities, or 7 possibilities for arranging the 3 sulfur atoms. So these are isomers. And they have different properties, but all of them have in common that this is a planar scaffold. And therefore, pi-pi interactions should occur, and this would be good for the whole transporting along the material. So we started with this because of the symmetry, C3 symmetry. Not all of them have been synthesized, okay? So it's not so simple from that viewpoint. And, we carried out the synthesis of these molecules with diarylamine or triarylamine derivatives, and also diarylamino connected to the carbazole. So all these subunits provide you the right energy alignment, okay, with the perovskite. So here you have the synthesis, was very simple, commercially available, iodination reaction, and from here is a palladium catalyzed Sonogasira cross-coupling reaction. This is a quite singular reaction at very high temperatures in which the formation of the thiophene rings occur, and from here, just introduction of bromine atoms. So relatively simple, in 4 steps you get your central core, and from here, it is possible to create a variety of whole transporting materials just by amination, Buchbach-Hartwig reaction. So, and here you have the BTT1, BTT2, and BTT3. That was chemical protocols, okay? And you see that all these BTT1, 2, and 3, they have the right alignment in between these electrodes for the perovskite and the gold electrode. So I will not go into detail, but just in case you could later on to discuss on that. Here you have the photovoltaic parameters. It was published in 2016. And at that time, look at this, the efficiency was 18.17. I guess that the world record should be around 20 or so, 20%. So no hysteresis was observed in this system. So they behave really very good, very nicely, and equal to the OMETAD material as well. So another possibility was just to modify, why don't we use a different position for the sulfur atoms? And in this case, we did it by using triarylamines, and we carried out this study. And you can see again that this is, well, you can see here, which is the scanning electron microscopy. You can determine here the layers for the perovskite device, and you can see roughly also the size of the layers. So in this case, this system resulted to be also of interest because the efficiency was also reaching 19%. And the argument, the reasoning for this is because now the two sulfur atoms are pointing to the same direction, and this probably is interacting with the perovskite and therefore improving the quality of the interface. So in agreement with this also, the best value was obtained both for BTT4 because the conductivity, the electrical conductivity resulted to be higher. So you can see here that is also, the idea was to synthesize molecules and to see by design if we could improve some of the properties. And well, the conclusion was that the isomerism also play a role, because when you have the sulfur position at different, in the central core, at different position with the sulfur atoms, you increase from 17, 18 to 19. Okay? Another possibility was to modify the nature of the heteroatom inside. And this was also published the year, 1 year later, with, you can see here, with nitrogen, oxygen, selenium, and sulfur. Without going very much into detail, you could see that all of them have the same behavior to a spirometad. Yeah, some of you could say, yeah, then it's the same behavior. Yeah, but remember, a spirometad is tremendously expensive. 1 gram, at that time, 1 gram of this material was around 500 euros, 1 gram. And it's difficult because you have to sublime. So this was not useful for practical purposes, for fabricating devices. So it was compulsory just to go to other materials. All these materials I show with you is roughly around 50 euros per gram, roughly. Could be improved for sure. But anyway, just to go to the current situation, the current challenges are written here. It should be important to improve the efficiency, but has already been achieved 27%. This is more than enough for practical purposes. Also improving the long-term stability. Now has been proven that 1 year can survive the devices. Improving the surface area of the devices, the mini modules, but here you can see some of them with efficiency around 16%, 30% per 30 centimeters. But also important for commercialization is improving the fabrication cost. So if we have to say which one should be improved, this would be probably this two system. So, and we did it. We addressed this question and we designed this new low-cost, long-term, stable spiro material. This was published, the first paper in 2021. And this was synthetically relatively simple to do because you can see here that from this commercially available, this was phenoxazine or thiazine, you can follow this interesting chemical reaction, but in 3 steps you can get this material. Okay, it was fully characterized. I will not go into details. And this is the cells we prepare in our lab at India Nanoscience. And you can see we did it with a triple cation perovskite with efficiency of 1836. Spirometad was pretty much the same. But notably, and these systems improve drastically the stability of the cell because it was, you can see here that our system was able to retain over 90% of the efficiency for more than 300 days. So it was around 1 year, and the stability was surpassing 90%. This is something completely unusual or never seen for Ometad. And this was at the ambient condition, room temperature. This is the humidity, relative humidity, 30%. And the evolution and the illumination was after 1,200 hours, okay? The efficiency also decreased only by 6%, so it retains 94% of efficiency. These were really fantastic, okay? And these were materials by design. But this was the first round. So why don't we improve the quality of these systems? And that is what we did, and these are the new Spiro systems. And we synthesize in our lab these materials, which the feature for these materials is that they are the same central core, but only with the phenothiazine, because the result is to be the most efficient one. So we remove the oxygen and we use only sulfur again. And this is interesting because look at this is the expected cost for 1 gram. And what is remarkable here is that now the molecules are asymmetrical, so they are not symmetric like the previous one. This paper was carried out in collaboration with Michael Gretzel, because we sent the postdoc to his lab for carrying out some experimental studies. And also with Enrique Ortiz, who is in the audience, and he is a theoretician, and he will give you a lecture, so I will pass this part of my presentation to him. And here are the thermal stability resulted to be very good for all systems because it's over 350, particularly very good for this with the naphthalene and fluorine. Take this in mind because fluorine resulted to be the champion but very champion, take in mind. This is what is much more interesting is to see the differential scanning calorimetry, because all the new systems have the TG values, which is over 150, which is significantly the glass transition temperature, which is significantly larger than those obtained for the spirometad, which is 125. So, and probably this is the reason because spirometad is not so stable, okay, because the relatively low glass transition temperature. So in our system, it resulted to be much more competitive, and you can see the absorption and emission spectra. And again, the interest was in this system having the larger pi system. And we also determined the electrochemical properties, and with this was also possible to determine the electrochemical band gap. So this is interesting for these molecules. The very good alignment, okay, in between the titanium, where this is the perovskite, typical perovskite we use in this case, and also the metal electrode. Interestingly, in this system, the perovskite was the FAPI, so the formamidinium lead 3 iodide, but in the synthesis was carried out with the 40% of methylammonium chloride. This is not to get a complex compound, because at the end, the methylammonium chloride disappears from the middle and you get the same compound. But also the interesting here was just to introduce an interface, which is the methoxy phenylethylammonium iodide, which is here. And these are the typical features. So here is the concentration of our systems, 35 millimolar versus the 90% of the other one. So the quantity is relatively much lower. And this is amazing because these are the PCE values reported. When we got this result, the maximum was 25.8. At that time, the world record was 26.2. So we were very close to the, however, it took us almost 1 year just to get all the results, repeat many things, and eventually the record was improved, was increased a little bit more. But these are fantastic behavior for these systems. And this is the stabilized efficiency, which resulted to be 25.4 for 5 minutes working at the maximum PowerPoint tracking, which is under very, very stringent, very strong conditions. So this is fantastic numbers and on the top of the efficiency for these systems. For the efficiency, but if we go to the durability and stability, you can see this is again in blue, which is the fluorine containing compound. So this is the efficiency of very higher reproducibility. And this was also certified by an independent laboratory, and you have here the result. The value, certified value, resulted to be 25.2. This is really amazing. It's very high, one of the highest reported that I will show you, but also in terms of, well, this can be accounted for according to the time resolved photoluminescence for this material, for the blue one, which was our champion system. Anyway, this is in order to account for these results, Enrique carried out interesting theoretical calculations, but without spoiling his results, simply to say that the idea is that the lithium in this compound is retained, is complex in some way with the aromatic part, in contrast to the other one, to the spirometad. And that means that the lithium is one of the drawbacks for the stability of this system. So the lithium is retained and don't go to the perovskite, okay? That would be the conclusion for this study. And in terms of, you can see here that in all of them, with the only exception of this case, the fluorinated one, they exhibit a very long-term stability under light continuous illumination and thermal stress. So this is really fantastic, one of the best in terms of those compounds reported. And they have been undergone to the ICO's protocols. This is for durability and also for under light illumination. So this data, and this is under stress. So this is, again, the maximum PowerPoint tracking with 60%, that is the relative humidity, 60%, and 65 degrees of temperature, which is expected the real conditions because of the heating of the sun. So this is just to compare what happened in this world, which was the fluorinated one, but the other one was really fantastic. The value is amazing. Many aspects. This is the hydrophobicity for this system was the best one. So this is also the naphthalene also was super. And this is one of the reasons of the best behavior of this system when compared with the Spiro in the presence of dopants. Because when the presence of dopants to increase the charge mobility, in this case you go from 187 to 153. So this is much higher if you consider that for the spirometad, in the presence of dopants, you go to 62 degrees. This is the main reason because of the lack of stability for this one. So I do not hesitate to say that we have probably one of the best, if not the best, whole transporting material reported in literature according to the efficiencies and stability. So just to prove this, the referee said, you must make fabricate a mini module. And that is one of the reasons because it was published later on. And also, this experiment was a time-of-flight secondary ionization mass spectrometry in this area, nicely support the theoretical study by Enrique saying that the lithium is decreased in the transporting material, thus preventing the presence in the perovskite. Also, experiment with the SEM. I will not go in detail, but you can see here that when you compare with the spirometer, this is the pristine perovskite, spiro, but when you go to the system with the fluorine, which is one, or this with the naphthalene, it's a little bit smoother. And this is the module, the mini module. It was prepared with a spiro and also with the fluorine derivative, and you can see here the behavior of one and the other. So, and this is the short phase. In all the studies, the mini module with our compound retain 85% of the initial efficiency after 1,100 hours under these conditions, which are really stringent conditions. So this is the reason because these results are approaching. You can see here the efficiency. This was the mini module. We reached efficiency of 22.07%, which is fantastic because it's 5 by 5 centimeters, okay? So this is a tremendous result in this topic. So this is, just to conclude, the key features is that we have chloride modified FAPI in combination with the presence of methoxy phenylethylammonium iodide. The efficiency resulted to be, this was the largest one. This is our champion, which is 25.8, but certified was 25.2. And this is for the fluorinated one, which is this champion molecule, because the design makes sense, okay? This is the idea. And retain 80% of the efficiency after 1,000 hours under maximum power point tracking, okay? These are the conditions by ISOS L3, which is the test protocol. And also the same molecule in the mini module, 25 square centimeters, retained the 22.07% and 85% of initial, again, under these conditions. So this is a fantastic result, nice results. And I want to conclude with this slide because this is from my close friend Prashant Kamat, who is the editor of ACS Energy. And the question is if the perovskite solar cells are reaching the efficiency and voltage limits. And you see that it was till 2023 actually. So, but this is in black. You see the single junction. So one device, only single device, like our device. And the maximum efficiency reported was around 26 or so, okay, which is our system would be around here as well. In terms of efficiency, in terms of stability, it would be, is not here, I will show you later on here. But this is in blue, what you can see here, the tandem solar cells. So maybe if we would need higher efficiencies, the tandem solar cells as silicon, probably silicon and perovskite would be the best one. So, and here is the certified efficiency, which are not always the same. But again, in black, you can see that this was in 23. In 23, it was 26.1. So this is for a single device. And these are again the reaching around 34. Now it's almost 35, having the tandem system. So probably the next decade will be the time for tandem solar cells and improving stability. no doubt the results we have obtained close perovskite solar cells close to commercialization, because it still is an open question in this topic. So I want to thank the people the group that have participated along these papers I show with you. These are our group, which is 3 chemists and 3 physicists. Okay, they are preparing the devices, so this is a multidisciplinary topic. They are working at India Nanoscience in this case. Professor Nasiruddin, and there was also, Iwan was the postdoc working with him, but also in the last results with Professor Michael Gretzel, and Jaeki Young was working with him as a postdoc. And also, the theory was carried out in Valencia in the group of Professor Enrique Ortiz. And also was participated, Jaeki at the same time stopped his postdoctoral stay with Michael, and he moved to South Korea. He finished the study in South Korea, so the Korea Institute of Energy Research made extraordinary efficient work in order to improve the efficiency of the material. They are expert in improving this one. So thank you to all of them, and thank you to you for your kind attention.
Thank you, Professor Martin, for a fascinating lecture and equally fascinating results and progress in the field. I think we have time for a few questions. Who can I invite? Yes, madam. Can you quickly go with the microphone? We are a bit in a hurry.
Could you see that the ladies are with the
yeah, please go
waving
on.
their hands, but only ladies. So thank you. That was because my previous question with you, only ladies. So.
Oh, is that so? Okay, let's do that debate on the coffee time. Please ask your question.
Thank you so much for your presentation. I really liked it and really enjoyed. I'm wondering for curiosity that what is the most important criterion for designing this whole transport material? For example, some of your BTT-based compounds has OMe, methoxy functional group, or the sulfur is inside of the structure. And what is the most criterion part that we should take into consideration that use especially for these materials? And the most important thing that is in my mind is the concentration of these functional group and what is their role for improving the efficiency. I will be grateful if you can.
Yeah, it's a good question, but it's a difficult question because after 15 years working in whole transporting materials, we got some interesting results. What you said about the methoxy substituents, this is a basic requirement in order to get the alignment. So the energy alignment is critical. If you don't have your systems at the right energy, aligned with the perovskite and with the electrode, then it doesn't work. So there are some criteria that are generally established. But from there, to get a material, because you could get a fantastic material, but you need 10 synthetic steps, is out of order, you know, and so there are many criteria. It's difficult to say in a few words, but it is like to prepare mayonnaise. Now I know that nobody prepare mayonnaise, is forbidden as well, but when I was a child, I did it, and when you surpass a limit in one place, the mayonnaise was destroyed. So nobody could say, beside these critical issues like energy alignment, but you have to think in terms of stability. If you want something to take on the roof, you have to take care with humidity, water, oxygen, temperature, and light. So you are dealing with all these concepts because it must survive. And don't forget that perovskites are salts. And salts, if you put it on the water, dissolve. That is because many of these solar cells are being under consideration for the spatial journeys, you know, because in the outer space
Super.
could be a
I think
chance.
this is a lot of thought for further discussions. Can I ask somebody else if there's a question? Yes, please.
Yeah, Monica is one of the expert people in this
Yes.
topic.
Thank you, Nazario. It was very impressive work. A lot of amazing results. Congratulations. My question is about the top seams analysis that you show. You say that you were able to see the lithium of the whole transport layer. My question is about the technique is okay for the solar cells. I mean, you don't damage the device. And the other one is that analysis were made in Madrid or somewhere else?
No, the optimization, yeah, we prepared the first paper I showed you published in 2021 that was completely done in Madrid, the fabrication of the cells, everything. But we realized that certainly we had something important. So that is because we started with the synthesis and the design and so on. So it was a long story to go there. And eventually we got in Madrid a very high result, close to 22%. But at that time, I had to send a postdoc with Michael Gretzel. This postdoc was working with him previously for 2 years, postdoc. And she was only 3 weeks. But it was not time enough for doing the experiment. So Jaeki, the postdoc, was also engaged. And some experiments were carried out in Switzerland, but the material and most of the basic experiments were carried out because our laboratory is very well equipped. But then Jaeki moved because the postdoc finished and he went to South Korea. This was fantastic. This was fantastic because they are very expert in improving efficiency.
Any other questions? I see that's not the case. Oh, yeah, one. Let's have the final question here and then we...
I'm just very curious about the stability compared to the spiral method. You know, the lithium definitely is an issue for them. But if they diffuse into the postcard layer, they would definitely want to destroy them, make them unstable. But yours, you see some reduction of them, that is definitely very good. But the other is that why using the spiral method, the morphology of this postcard is worse than this using your whole transporting materials. That is my questions. Because usually, if
Can you formulate it shortly? Because otherwise we will not have coffee.
Yeah.
Yeah, stability. Still the stability. Why it's better than the spiral method?
Well, the main reason is, one of the reasons is because lithium is prevented to go to the perovskite, and also because this in the 2D material, the methoxyphenylethylammonium, the molecule, the whole transporting, our molecules interact very efficiently and they go by the aromatic side inside. And this gives the interface in between the whole transporting and the perovskite is significantly increased. So many defects and many results related with quantum yield come on. There was all the experiments that were carried out, the quantum yield efficiency resulted to be much higher when you have our material. And that is because the surface has many pinholes and many defects, you know. So the surface is much better with this material.
Thank you so much.
We can discuss later on.
There is
okay?
plenty of time to discuss in the coming days. Take advantage of it. The speakers are here. We have a 15-minute break. We have coffee. And please let me finish this session and join me to thank Professor Martin again for a wonderful talk.
And join to me the session. Okay.